So, as we wait for everybody to join back in, if they are able to join back in, what we have here on slide 13, is how we can kind of combine the two tests together. Some of the given information here with. So, what we know here about being concave up and concave down and critical numbers. So, if we have a 0, if our function is 0 or function does not exist when C, so C would then be a critical value, right? So this would also allow us to open up an interval that contains all of these. So if we have something that is concave up, and there's some C value, some critical value in there, we're looking at this being a relative min. If it is concave down, we're looking at this being a relative max. We talked about that before. Concave up means mins, concave down means maxes. If it is 0, then the second derivative test is going to fail, and therefore we must go back to the first derivative test. Does that make sense? This isn't that different than what I was already telling you guys before, but I just want to make sure that we're clear. Okay? So, the important thing here is that when we're looking at this, so we have a function where we have a specific value that is a 0 of that function, or does not exist. So where we cross the x-axis, or of course where we have a vertical asymptote, where this value also happens to be a critical value as well for our derivative. So there's a couple of things here that have to work in tandem for us to truly know if this is actually going to be a relative min or actually going to be a relative max. So we can say that looking at the second derivative test, but for us to do that, we need to have a little bit more criteria at the beginning. Does that make sense? Got to test a few more things before we start doing all the other stuff. All right? So, I'm all out of sorts here because everything's not working right today. Because why would it? Scotland has not been having a good past couple of days. Okay. At the very least, I'll have another recording of us doing this, so I won't have to record it again later. So, we're going to go ahead. We're going to determine the values here of the extreme. We're going to talk about determining the relative extreme. We're going to use what we just talked about. Basically, we're going to run exactly what we have been doing, but we're going to do a few steps. So let's use the second derivative test if this is possible. The first thing we're going to do here, of course, we need the first derivative. Okay? We need the first derivative. So let's go ahead and let's get that here just to double check what we have. So looking at example 5, we have negative x to the 5th plus 5x cubed. This is our beginning function, of course, so we'll go ahead, take the first derivative. What are we looking at here for first derivative? Should be negative 15x to the 4th, correct? Plus 15x squared. Are we all set? Okay. So what we are going to do is we are going to find the critical values. So for us to do that, of course, we need to set this equal to 0 and solve. So, or, of course, where this one does not exist, but that's not going to yield us anything here. So 0 equal to negative 15x to the 4th plus 15x squared. I'm going to factor out a negative 15x squared because that's a GCF here. X squared minus 1 is what will remain. Yes? So this actually is going to give us 3 zeros here. This is going to give us 0, 1, negative 1. These are the values that we are concerned about here. These could be relative maxes or mins according to what we might have. So, let's go ahead, let's continue on here. Next step. Let's do what? Let's do the second derivative. Okay, let's do the second derivative. So what we've done so far, we did the first derivative to find our critical values, because what we're going to do is we're going to put it all together, right? We're going to use our concavity, and we're going to say, okay, this is a critical value somewhere in this concave up or somewhere in this concave down. That means that it's a min or a max, right? So let's go ahead. Let's get our second derivative here. So second derivative. And the nice thing about doing this is we already have the first derivative like 3/4 of the way done. So if this second derivative fails, we can always go back to the first derivative test and finish it out. So second derivative function here, that 4 is going to come down. We're looking at negative 60x to the third. That 2 is going to come down and be 30x. Are we good here? Okay, same drill as before. We'll set this equal to 0. It does not exist. Of course, equal to 0. Does not exist. Now, does not exist isn't going to yield anything for us here. But this one will, of course, 0, negative 60x to the third plus 30x. I'm going to go ahead, I'm going to factor away a negative 30x, and leaving behind, that'll be 2x squared plus, or 2x squared minus 1. Are we all set here? Okay, that is not going to factor very well for us. That is not going to factor very well for us. So, let's go ahead. Let's continue on here. I'm sorry, I'm all discombobulated. Let's get a second here. All right, so we've got our second derivative. What do we do? Second derivative test is possible. We don't need to do this. Sorry. Yeah. We don't need to do this. My bad. All this. Okay. What we're going to do now is we're going to put these in. My fault. My fault. So let's start with double prime of 0. 0, 0 equals 0. So for 0, the test is going to fail. We're going to have to go back to the first derivative test to figure out whether this is a maximum or minimum. If we put in 1, what does this tell me? Well, this is going to be negative 60 plus 30. That's going to be negative 30. So since the second derivative here is negative, that tells me that this is going to be a max. So a max at negative 1. If I do the same thing for 1, or excuse me, for negative 1, I'm going to also end up with negative 30. So I'm looking at a max there as well.
I have positive 30.
For negative 1?
Yeah, because it's
negative
60
positive 30.
x to the third.
Yep. Positive 30. So that's a min. It's a good thing you guys are here. So that's a min. A min. This calculus is full of mistakes here today. Can't seem to get back on track. So let's recap what we've done before we go back and finish up here. So I did my first derivative test. That's what we have here in green. I got my critical values, 0, 1, negative 1. We're going to take these critical values, we're going to plug them into the second derivative. Second derivative right here, evaluating all three. Evaluating all three. So, because the second derivative is negative here, that would imply that at this point we are concave down, right? So shaped like a frown. That's why it's a max. And then over here, because we have a positive value, that implies that the second derivative would be positive, so concave up, meaning a bottom to the value, a min, right? So it goes back to this one here, 0, then it failed, right? So how do we figure this one out? What did it say before?
We'll use the first derivative.
Gotta go back to the first derivative test, right? Gotta go back to the first derivative test to figure out what's happening around 0. So if we want to, of course, we'll just pick that up. And I don't even need to do the full number line here. I just need to focus on what's happening before and after 0. Before and after 0. So before 0, if I put in a negative, let's put in -1, because it doesn't, well, let's not put in -1. -1 is the critical value. Let's put in like, let's put in 1/2. Let's put in 0.5, right? So if I put in 0.5, -0.5, what's going to happen here? So 0.5 to the 4th power times -15 plus our 15 times 5. And I get positive. And we plug in the other side. Let's plug in a positive 0.5 times -15 plus I also get positive. Positive and positive, right? So what does this tell me? Not a max or min. Not a max or min. Questions here?
So that's all we're going to do.
Yeah, we just go back and double check the other value. Go back and double check. Okay, let's try this one out. Mr. Coffin will try to refrain from making mistakes this time. Okay, so let's try this again. Let's try this again from the top, and let's see if we can make this a little bit better for everybody. Okay, so why don't you guys help me out, because obviously I can't be trusted to do it correctly anymore. What are we going to do? We need to do the first derivative. Okay, what is the first derivative? Chain rule, right? Okay, so what's going to happen for our chain rule? This negative is just a multiplier, right? So what's going to come down and join it? The 2. So we're looking at -2 out in front, right? What are we going to have inside? It's unchanged inside, right? Should be x minus 5 to the first, right? Or don't really need the exponent there. And we would do what else?
The derivative of the inside, which is just 1.
Which is just 1. So this is my first derivative then, right? Relatively easy chain rule here. Okay, now what are we going to do? We want the crit values of this, so of course we're going to set this equal to 0. Which really we're just going to focus on the x minus 5 being equal to 0, so x equal 5. Are we all okay with this? Okay, let's double check with what we have here in our blue box. In our blue box, we're looking at, I see some people have been able to rejoin the stream, so we are on slide 15 for anybody who's lost. So, got our first derivative, got our critical values from it, x equal 5, yes? Next step here is go to the second derivative, so we need to get our second derivative up here. So when we do our second derivative, what are we going to get here? If you want to make this easier on yourself to do the second derivative, distribute that through -2x plus 10 if you'd like to do that. Distribute that -2 in if you find that to be easier. When we do the second derivative here, what are we going to have? -2. It's a constant, isn't it? It's a constant. Yes? No? Maybe? I'm not sure why mine says 1 up there.
Yeah.
That's just probably a mistype by me. Yeah, because it's all wrong. It's all wrong. Great job, research. You got on fire today. Just absolutely stellar. So, let's go ahead. Let's finish it up here. Of course, when I plug in 5, I'm going to get back -2, right? This is a constant, right? So it is negative here. So that implies what? That we are concave down, right? So we're looking at a max at 5. Questions here about this one? Concerns here about this one? My slides are all jacked up. I'm all jacked up. What else can we say? What else can we say? Okay, let's double check, make sure Mr. Falcon didn't make any mistakes here about last. Yeah, I don't know why I have that there. So, Mr. Kaufman just got typos on his slides. I swear I changed that this morning, but I guess not. Let's do that number 7 there, even though it's not in the slides, just because we keep on having issues. Mr. Kaufman keeps having issues, and we have time. And I feel bad for the students that missed out on their live stream, so we can do another problem or so. So let's go ahead and let's try this one out. It's going to be a little bit tougher. X squared plus 1. So let's do the same drill here. We're going to go ahead, we're going to run the first derivative test to get the critical values, and then we're going to do our second derivative test if it's possible, right? To go ahead and tell us whether it's max or min. Okay. Now, there's a reason why I don't normally do this one, because it's kind of a beast. Not gonna lie. But since I keep making mistakes, I promise I will try to get this one right. So, first thing we need to do here is start by taking the first derivative, which is actually the easiest part of this problem. Well, one of the easy parts of this problem. First thing we're going to do is we're, of course, going to rewrite this. So that way it reads x squared plus 1 to the 1/2. So when we take the first derivative here, we're going to have 1/2 times our x squared plus 1 to the negative 1/2. First exponent coming down, decreasing by 1. And then we need to multiply by the derivative on the inside with our chain rule, which is 2x. Agreed? Yes? Okay. So these 2's are going to cancel, and this needs to go onto the bottom of this fraction. So when I'm looking at my first derivative, I'm looking at x over the square root of x squared plus 1. Is everyone okay with this as our first derivative? Bianca says yes. Maddie, what do you think? Yeah. Fatima, you on board? Callie? Great. Okay. So we need to talk about this one. We need to run our first derivative test with it, right? Find our critical values. Okay. So f first derivative equal to 0. Well, that's going to be when our numerator is equal to 0, yes? Which, of course, is when x is equal to 0, right? So there's one of our values. Okay. Is there any point where this function does not exist? So we did equal to 0. Is there any point where this does not exist? No. There's no way for me to get a negative out of here. There's no way for me to set this equal to 0. Because I need the root to go to 0, which is not possible because when I take x squared plus 1, I'm going to get x equal to plus minus square root negative 1. Or plus minus I, which is not what we want to be dealing with right now. So there is no point in time where our first derivative does not exist. So we only have one value we need to test. Okay? Problem being there, of course, is now setting up the second derivative. So this is going to be f and g. Now here's the easy part, of course, is g's derivative is already done. It's what we already have up here, because that's the same function I started with, right? So don't kill yourself for redoing the work. Make it easier for yourself. F's derivative, of course, is 1. Okay, so when we set up our quotient rule here for the second derivative, we're looking at g squared, g f derivative, minus f g derivative. So on the bottom here, we're going to have square root x squared plus 1, quantity squared. On the top, the first part's going to be easy. We have square root x squared plus 1 times 1, so it's just going to be the root, minus f, which is, of course, our x, times the derivative of g, which is the first derivative, the monster we're already dealing with. So far, so good? Okay. Now we got some things we can simplify here. We can cancel this root and this power. Gives us x squared plus 1 as our numerator. We can put this together, and we will. I'm going to multiply the top and bottom here, by this root to get to a common denominator. That's going to give us x squared plus 1 over square root x squared plus 1. And I'm just going to multiply these x's together, minus x squared over square root x squared plus 1. Are we okay with the steps I've taken so far? So I canceled my root with the power on the bottom. I made common denominator for the first term, and I just multiplied my x into the second term. Are we all okay with what I've done for my second derivative thus far? It's a little bit complicated here in the second derivative with this quotient rule. That's why I normally skip this problem. But you guys have been doing better than me today, so let's go ahead and let's simplify this out. I can cancel these x squareds, and that's going to leave me 1 over quantity x squared plus 1 times 1 over x squared plus 1 when we unstack those. which seems more complicated than what it is. We're just going to write them together. X squared plus 1 as a group, square root of that same group. Now, if you want, technically, you could put them together. Technically, we could put that together. This is power of 1. This is power of 1/2. We could make this 3/2 power, which is how we get to those, where we have a cubic inside and something on the outside. However, we're kind of circling around here. We don't really need to go to that route because ultimately we're going to take our critical value, our 0, and we're going to plug it in. So now that I have it relatively to a point where I can do that, I'm not going to kill myself continuing on. I'm going to slam it in and see what happens. So when I put it in, I'm looking at 1 over 0 squared plus 1, square root 0 squared plus 1. By my estimation, that's 1 over 1 times square root 1, which is 1. Yes? So this is positive here. What does that tell me about at 0? Because this is positive, what are we going to have? We are going to be what? Concave up or down? Up. So that means a min at 0, right? And if I really want, we can plug it back into the original. And that tells me, of course, that it's 1. So my min is 0, 1. We have a min at 0, 1, at the point 0, 1. Questions here. I know that I made a lot of mistakes here today, and I do so apologize. This was supposed to be an easy finish up, and it turned into something that was definitely not, between the live stream crashing and Mr. Kopp making a plethora of mistakes. But I hope that we're on the same page now. Questions here. In essence, what I wanted you to learn today is you can take your critical values from your first derivative test, put them in, and if they give you some type of answer about concavity, that should lead you to knowing whether they're mins or maxes, which is something we kind of talked about before, but I haven't showed you how to test it. So now you know how to test it. Questions here or concerns here about this? Okay, your homework is on the next slide. At risk of putting myself into more jeopardy with more problems and more issues, I'm going to go ahead and just let you have the rest of the time to work on your homework. As you hear in class, I'll put it up for you, but it should be the last slide on Canvas. The last slide on Canvas. Look at page 195. For those of us on our live stream, I do so significantly apologize. I don't know how many of you got the chance to rejoin, but I will make sure both videos remain available for you all. And I do apologize once again.
What if we already did?
Huh?
What if we already did?
Well, then I guess you're just done for the day, Callie.
Okay.
And I will see you all next time. Those of you on live stream, you guys can go ahead. Peace out. I'm going to end the stream here in a minute. Unless you guys have any questions or want me to go back over any problems. If so, you can type them in the chat there.